Well, okay, good morning, and welcome back to the second day of this round of lectures, and welcome John Cardy, who's joined us now. So we were talking about critical phenomena, mostly about statics and thermodynamics yesterday, and I just got started with a little bit of critical dynamics, which will be the feature of today's talk. In our tutorial discussion session, we addressed a few questions. It's great to have those coming. Please keep up the good work and ask me during the lecture and during breaks and lunch and dinner and whenever you can catch me. And I'll be glad to discuss that because we really want to make sure that in this school, we don't lose you on kind of the first and second lecture. You really need to stay with us. And so we don't need to cover everything we had maybe planned. It's a lot more important that you take away those things that you really understand and can follow. So I've tried to write down a little bit of a summary of what we discussed yesterday. We did start with the Landau expansion of the free energy density for a continuous second order phase transition. I'm still trying to figure out how to not fade out of this microphone. Okay. And then a generalization for that if you wanted to address fluctuations, which I was arguing are important for critical phenomena. And so for a generic second order phase transition, assuming an ON symmetry for the order parameter, which is a special case, so it depends on the symmetries that you're looking at. But assuming this, we wrote down this Ginzburg-Landau Wilson Hamiltonian, which I was saying is not really a microscopic Hamiltonian, nor is it a macroscopic free energy, is a mesoscopic description in between. And we can kind of stop this expansion in terms of S squared, that's demanded by symmetry, at this fourth order term, as we were arguing, and this gradient square term punishes you for spatially inhomogeneous fluctuations. There are rare cases where fluctuations are actually favorable in the free energy. That happens in type 2 superconductors, for example, but we're not addressing that here. Okay? And what this Hamiltonian means, it's really giving you the equilibrium canonical probability distribution. That is the meaning of this. So if I have a configuration S of X, this tells me how likely that is to be found in thermal equilibrium. Now we're going to go away from thermal equilibrium at some point, but for now this is what we have. And then I was telling you, and that's a highly non-trivial statement, that in addition to a kind of thermodynamic scaling for the free energy density that we discussed, there is scaling for the correlation functions. And that can be extended to dynamic scaling for the order parameter, so a one-point correlation function, if you like, and two-point correlation functions, and so on. So here is the scaling form for the order parameter. I set the symmetry breaking field H to 0. There you can add that and get the kind of standard form for that as well. And so this contains some temperature dependence, which I chose here to pull out with this kind of static tau to the beta. The beta is the order parameter exponent factor in front. And then we're left with the time dependence inside the scaling function. And in that time dependence, there's a characteristic time scale, which typically is a relaxation time scale. Doesn't have to be, but typically is. And that relaxation time diverges as we approach the critical point. That is the fundamental phenomenon of critical slowing down. So as you get larger and larger correlated regions, the size of which is determined by this correlation length psi, psi itself diverges with a scaling exponent we call nu, and almost everyone else calls that nu too, which is good because there are some notation issues in this field. And then the typical relaxation time goes as psi to the power c, so it diverges with tau to the minus z nu. Okay? That's an assumption, of course. It tends to be the case, it tends to be true. It's not always a power law. There are cases where you get exponential divergences or other variants, but in many systems these are power laws. If that is the case, I can generalize that to writing down a scaling form for a dispersion relation in the vicinity of the critical point. As we were discussing in the tutorial session, you don't quite know how close you have to be to the critical point to find these scaling phenomena. But somewhere in that scaling region, you will have that. And then you can pull out an overall factor, for example, of q to the z, and you're left with a scaling function that's a product of wave number, or wave factor magnitude, and psi, because that's a nice dimensionless quantity. Okay? And I can put this all together and write down a dynamic correlation function scaling hypothesis. So this is the order parameter at position x and t, correlated with the order parameter at position, in this case, 0 and time 0. In general, there are two positions, two times. If you're in a stationary regime, which you are in equilibrium, then the correlation function at two positions, two times, will only depend on the difference between the position vectors and the time indices. Okay? That will not hold in a situation I'll discuss a little later today, but here it is. So in fact, there's really only separation distance in time on which this depends. And then I can pull out this overall algebraic decay, which tells me how the correlations decay right at the critical point. That's the meaning of this exponent eta. And then we have a scaling function where you measure distances relative to the correlation length and times relative to, again, this overall time scale log psi to the z. Now, if you stare at that, it looks like I have a d-dimensional theory plus another time direction. So it looks like a d plus one-dimensional theory with, however, anisotropic scaling. In the position directions, I have to scale things by xi. In the time direction, I have to scale things by xi to the z. So if I think of a d plus one-dimensional setting, time, of course, has special issues like causality and the like, but if I think of d plus one-dimensional settings, this dynamic exponent z takes the role of an anisotropy exponent. It tells you how you have to scale things differently in time. So if I'm in a relativistic setting, z would be 1, and actually I have kind of space-time symmetry, the same scaling in both directions. Okay? I'm just mentioning that because I think John will be addressing some issues like that next week. And I can Fourier transform that in space and time if I like, or only in space or only in time, so there are various equivalent versions. And if I do this from the spatial integral, I'm picking up another factor q to the d, or xi to the d, let's say q to the d. From the time integral, I'm picking up a factor q to the z. And then overall, as I do this, I get 1 over q to the c plus 2 minus eta. And I hope I did that right last night in the tutorials. Okay. And then you're left with a scaling function. We get q psi and omega psi to the z. Now, the static limit for correlation functions is both your order parameters are taken at the same time. So for the correlation function, as I define it here, the static limit is at time equals 0. Okay. This is roughly how far we got yesterday, and so are there questions? That's because you're looking at equal time correlations. That's just the static limit. So once you have things at different times, you get dynamics in the game. But if I look at the same time, and I'm out there in equilibrium where things are, time translation invariant, then that is the static limit. Critical slowing down means as I approach a second order transition, I get large correlated regions. So for example, in a magnet, in a spin system, say Ising magnet, you don't have individual spins fluctuating, but you have large clusters going back and forth. These large clusters are of the typical size of this correlation length. Now you try to flip a large cluster by any kind of dynamics you can dream up, which is not artificial, so it's not a cluster dynamics that you invent. But by individual spin dynamics, this is going to be really hard to relax such a cluster. And so this is a phenomenological description that tells you as these clusters grow, the corresponding relaxation time grows. Okay, and we'll have to try and determine what this exponent might be for different cases. It's not an argument, it's more an analogy. So if I think of space-time, which is a little tenuous here because the time direction really is not a space direction in this case, because you have causality in the game and things like that. But let's ignore that. Right? Just think of space and time's coordinates. I have this is an isotropic system by construction. I could have looked at different ones, but this is isotropic. I scale all my space directions by xi. I scale all my time directions by a characteristic scale in the time direction, which is this Tc. But Tc is not proportional to xi, it's proportional to xi to the z. So that takes the form of what's called an anisotropy exponent. Deviation of z from 1 tells you that you have to scale anisotropically in space-time. Yes. It's the analogy to anisotropic spatial scaling if I had different correlation lengths in different directions, which we will encounter later today, so I thought I mentioned that. Okay. All right, any other clarifications at this point? Okay, excellent. So something I kind of mentioned in passing, but I really like to emphasize is going back to this static part of the critical phenomena is universality classes. So what we did look at is kind of mean field exponents. So, we wrote down this Landau expansion, and we basically by power counting or dimensional analysis, inferred beta is 1/2, alpha is 0, gamma is 1, delta is 3, all these things. Or equivalently, eta is 0 and nu is 1/2. Those are correct results as far as the exponents are concerned if I am what is called in dimensions larger than the upper critical dimension. That defines the upper critical dimension. It turns out for this Ginzburg-Landau-Wilson-Hamiltonian that upper critical dimension is 4. So if we did live in an 11-dimensional world as in string theory, we would be good. Field exponents are fine. There's still fluctuation corrections to all kinds of amplitudes and correlation functions, but the scaling exponents are adequately described by the mean field approximation. That is not true if we live in our world where things are compactified to 3+1 dimensions. So in 3 dimensions, that is just not the case. And you both in experiment and simulations measure exponents that deviate from the mean field values. Okay? And that signifies this upper critical dimension. Right at the upper critical dimension, you get logarithmic corrections to the mean field exponents, which I won't be talking about much, so just for completeness, let me mention that. And I told you that you can use the renormalization group to have an analytic tool to systematically compute these exponents, show first what the upper critical dimension is, show which of terms are relevant and need to be kept for an analysis, and then compute exponents in a systematic expansion, for example, about this upper critical dimension, which is then a small expansion parameter. There are other schemes. There are non-perturbative RG approaches and other approximative schemes that can work very well. Okay? But that is the meaning of this upper critical dimension. And then it turns out that below the critical dimension, the exponents that you actually compute only depend on the spatial dimension via this parameter epsilon, the number of order parameter components. So that's the fundamental symmetry you have demanded of your system. And maybe if they are present long-range interactions, which are a tricky situation, as some of you know. They do not depend on other kind of microscopic details. They do not depend, what the overall scales here are, precisely what physical order parameter I look at. Is it a magnetization? Is it, as in superfluid helium, some complex wave function? If they have the same number of effective components, 2 in this case. They do not really need the precise value of this microscopic coupling U, because things are described by some fixed point value, which establishes the universality. Okay? So the exponents actually don't depend on microscopic parameters. What does depend on microscopic parameters is where the critical point is, what the value of TC is. How close you have to be to TC to find these scaling regimes, and the amplitudes of corrections to scaling, the next terms. So we just mentioned that, so we have that out of our system. And so what we are going to be asking is, what about dynamics? If I now impose dynamics, on what things will the dynamic exponent Z, for example, depend? Do I actually get away with a single dynamic exponent if I have more than one set of dynamical variables I need to worry about? Okay? So that's the issue of critical dynamics. Another quantity we're going to look at is dynamic response functions. So if I do this in Fourier space, Q and omega, this is nice because I just need to take the order parameter at this Fourier components and take a partial derivative with respect to the external field at the same Fourier components. If I do this in space and time, it's a functional derivative of C of x and t by d of h of x prime and t prime. So things are easier in Fourier space, so this is why I wrote this down. And then I can write down an analogous scaling form for dynamical response functions, pull out this factor, which is again the static behavior of the static response function, thermodynamic susceptibility, and then I get the usual kind of arguments. Okay? In equilibrium, this object and the dynamic response function, correlation functions are not independent. There's a fluctuation dissipation theorem, which you can derive in the framework of linear response theory. Or in weaker versions, you can derive that by means of Langevin theory, and we'll see this in play later. The susceptibility is given in terms of the time derivative of the correlation function, the minus sign. These objects have to be causal. I cannot have a response before I kick my system. So this is where this theta function comes from. Okay, so only for positive times, if I kick the system by switching on an external field at time 0, I can only get response for positive times, which is where this step function comes from. And then otherwise, it's just a time derivative. Or in frequency space, it turns out the equivalent version of that is that the imaginary part, that is the dissipative part of the susceptibility, is related by 1 over omega to the dynamical correlation function. That second version is why it's called fluctuation dissipation theorem, because as I said, this is the dissipative part of the response. These are fluctuations and they're intimately connected. If I'm away from thermal equilibrium, this does not hold. That's a signature of thermal equilibrium, very strong statement. Out of thermal equilibrium, response and correlation functions are fundamentally independent objects. Okay? All right, so this would be the general setting. With this, I'd like to kind of start and actually give you some explicit models to play with, so maybe all this makes a little more sense, and of course we're going to treat them very approximatively. So how do we describe critical dynamics in a continuum setting? We like to write down some equations of motion that give us, the dynamics. And obviously what we're interested in is the order parameter. So we'd like to have some equations of motion for our order parameter. Okay? What else do we need to worry about? Well, there's all kinds of other dynamical variables. But here is something that really helps us and assists us in constructing a phenomenological theory for this, and that is critical slowing down. Critical slowing down affords us of the really slow time scale for the order parameter. So anything that fluctuates on time scales much faster than the order parameter is going to look like noise to our system. Okay? So if I'm sufficiently close to TC, anything that is not the order parameter, and say something else we're going to discuss in a second, is just, some fluctuations in the background. And since the characteristic scale for order parameter fluctuations is large, these background fluctuations will basically happen on a very short time scale. If I call it short time scale, I can call it Gaussian white noise. I don't even have to worry about finite correlation times. So by means of, by exploiting the phenomenon of critical slowing down, I'm afforded almost for free with the justification to write down a Langevin type of equation for the order parameter dynamics. Okay. So this is for the slow variables in the system. Slow dynamical variables. And these are clearly the order parameter. But there are also clearly any other conserved modes, which you would normally call slow modes in a hydrodynamic. That's called continuum description. Because those are related to conservation laws. Conservation laws come with a continuity equation. And we'll discuss that in a few minutes. And that means that, at low wave vectors, the frequencies of these things have to go to 0. So these are slow too in the long wavelength, large scale limit, which is where you need to worry about for critical phenomena. So I need to worry about potentially coupling of the order parameter to conserved modes. But that's all I need. So in this sense, this is somewhat analogous to equilibrium thermodynamics, where you know that the only things we need to worry about in your Hamiltonian are conserved modes. We have to add the order parameter for the dynamical description. Right? And so now the question is, the order parameter, pardon? The dispersion relation? Oh, we'll have to talk about that. That depends on how things look. We'll get there, okay? That's exactly what we're aiming for, because once we have the dispersion relation, we know what these exponents are. So that's exactly the question we're heading to. Thank you. So now it depends, right? The order parameter itself could be conserved. It's spatial integral, that is the q equals 0 wave vector mode could be not changing under the dynamics. For example, for a ferromagnet, the total magnetization tends to be conserved. It could be non-conserved, which is a different story. So we have to make that distinction. And we have to worry about coupling the order parameter to other conserved modes. Well, the one you always have is the total energy. So does that matter? Okay, and we'll talk about that too. And then there might be other ones that this thing can couple to. So what you expect is that these static universality classes might be splitting up in different dynamical universality classes that depend on these kind of conservation laws and potential couplings. We'll have to worry if these couplings matter or not. I will not be walking you through all the possible models and classification schemes that have been done, but I'll give you a few kind of characteristic examples to give you a flavor of what can happen. Okay? So let's write down, to get this started, the simplest possible model. And it turns out to be, quite ubiquitous, even out of equilibrium, and I will argue about that too. And that is purely relaxational kinetics. So what I should say here is that other modes, everything else, degrees of freedom, are considered fast, and so we just treat them as Gaussian white noise. White is there fast, so we don't have any characteristic time scale that we worry about. That's true in the limit of, severe critical slowing down. Gaussian is just the assumption of least knowledge. As I'm not going to care about these modes so much, I'm just assuming the simplest possible scenario for the correlations, and that's Gaussian. Because of this, because the relaxation time diverges as I approach the transition. If I'm not near the transition, it's not. But sufficiently close to transition when critical slowing down kicks in, I can exploit that and treat it as a really slow variable. Okay? That's the crucial ingredient here. So thanks for asking again, so we have that down, because that's important. Correct. Yes, and we'll discuss that too. Its behavior will change near the critical point though, and we'll discuss precisely that in just a few minutes. Okay? So this is great. You guys are identifying the correct questions to ask, so now let's see what we can say about it. So the simplest equation I can do is, so I have these order parameter fields, and I want their time dependence. Now I'm assuming I'm in overdamped situation, right? We have very strong relaxations. For now, I'm ignoring that there is some reversible time dependence in the order parameter. We'll fix that later if we need to. So I'm assuming, that was too fast, I'm assuming purely relaxational kinetics. So an overdamped situation where a time dependence, if I disturb the order parameter, perturb it away from thermal equilibrium, it's just going to relax back. So if it's going to relax back, I'm just going to write down a relaxation equation. So there is a relaxation rate I'm going to call D. And I'm going to use the Hamiltonian here, pseudo-Hamiltonian, as the potential that tells me how the order parameter is fluctuating. And so the order parameter is seeking out a minimum of this potential. If it's not in the minimum, it's going to relax back. So it's going to look at like a force. Let me just first write this in this form. If this were just a function of S, it would just dH by ds, alpha. And then I would add this Gaussian noise. But this is a little more complex because I have these fields dependent on all these spatial variables. These are fields, they depend on space. So like this discrete variable, there's a continuous variable in there. So these are functions of x and t. And that means I need to actually change this. And remember, this was a functional. And I need to change the normal derivative to a functional derivative. But if you discretize these things back out, it would just be a normal partials. Okay? So that's just a formal variant of this. And then, of course, my noise will also depend on where I am. So this is purely relaxation kinetics. I need to specify the noise. Specify the noise. I'm doing noise averages, and what I'm assuming is that on average, any kind of systematic parts, any kind of forcing, systematic forcing is included in what I have here. So the average of noise should be 0. Otherwise, I'd actually have to add it back up there. The angular brackets here mean averages over noise histories. Right? This is not an average over a canonical distribution because I'm doing dynamics. What I'm doing is I get some realization of this stochastic process, C alpha of x and t, as function of t. So I get all kinds of variables of t. That's one noise history. And then I'm following the time evolution of these things in an ensemble of such noise histories, which is sufficiently large. And that is what I mean with these averages. Okay? And then there is, of course, the correlation, C alpha, how did I call this, beta? Mess up my own notation here. X prime and T prime. So I'm looking at how noise realization at position X and T is related to X prime and T prime. And I said we assume this is going to be Gaussian white noise. So we only get a contribution at the same position in space and time. It's supposed to be diagonal too. So only if I'm kicking the same direction in order parameter space. And in front here is a noise strength. And I'm going to set the noise strength to twice the dissipation rate and kT. That is because I want the system to be in thermal equilibrium. And I think last week you learned that if you have Brownian motion, the noise strength is related to the relaxation constant by an Einstein relation. If you want the system to relax to thermal equilibrium, you see this by writing down the corresponding Fokker-Planck equation for the associated probability distribution for that stochastic process. And if you want ST to infinity to reach this one, you need to have that relation. You've seen this last week, right? We'll also get back to that sometime later, but not today. So for now, let me just impose that. So this is imposing an equilibrium Einstein relation, or what's sometimes called a fluctuation dissipation theorem of the second kind, because on the Langevin equation language, this one will actually give you this one back. Okay. And we'll see that. So this is our description. Questions so far? This is for a non-conserved order parameter. Let me write this down explicitly. We're going to need this later. If I do the functional derivative explicitly with the Ginzburg-Landau-Wilson-Hamiltonian here, so I need to do dH by ds, this gives me a tau s. This gives me a u over 3 factorial, because there's a 4 here, s cubed, or s squared s, minus h. The functional derivative of this one, well, either you do Euler-Lagrange and be careful, or you're slightly more sloppy and you just do inside this spatial integral an integration by part. And you see this is equivalent to minus s Laplacian s. And then d by ds just gives you the negative Laplacian. Okay? So let me not go through this in much detail, just write it down. So this is tau minus the Laplace operator plus u over 3 factorials, which is 6 s squared, and then all this times s alpha. And then from the external field, we have a minus h. So this is going to be, I'm just pulling this out explicitly, dh alpha. And then we have the noise term. And I'm too lazy to write down the x and t's. Okay? All right. So let's look at conserved fields. And I was already saying we need a continuity equation in this case. So there's some density for these conserved fields. Maybe these are scalar fields. I'll just do this for now. And so this would satisfy a continuity equation. So there's some conserved current density. And that needs to be 0. So if I Fourier transform that, with the same convention that I have down there, so this goes as e to the minus I omega t, d by dt gives me minus I omega. This gives me an IQ, wave vector dotted into j of q and omega. And so we already see that the dispersion needs to be at least linear in q. So if q goes to 0, the frequency will vanish. Typically, these currents are in terms given by some relaxation rate and the gradient of maybe dh by d rho or something, the simplest case just by rho. In that case, you can plug this back into here and you see you end up with a diffusion equation. d rho by dt is going to be equal to d times the Laplacian of rho. In that case, the dispersion relation is just minus idq squared. And I hope I get the sign of this minus right, I think it is. Okay? So this would be the simplest possible scenario, and you get diffusive relaxation. So not just a uniform relaxation constant, but you get a relaxation rate that vanishes as q goes to 0. Now already for diffusion, we can go back to kind of this general dynamic scaling, and we see that if I go to this ansatz here for diffusion, the dynamic scaling exponent, if you like, is 2. Right? That is exactly what actually Sid showed us very carefully in the scaling form for the diffusion equation yesterday. That was basically exploiting scaling forms like that, where the dynamic exponent z was set to 2. And he showed us powerfully how you can actually then solve even for the scaling function just with that ansatz. Right? There is what? Yes, so that just means that things are relaxing, right? So this goes into e to the I omega, into minus I omega t, and so with the minus I it means e to the minus dq squared t. And we'll see that, right? So it just means relaxation. With a relaxation time, that's 1 over dq squared. I'm just kind of shortcutting this a little bit because we're going to see this more explicitly in a second. So if I now have a conserved order parameter, I need to modify this equation because that can't be right. The best I can have is a diffusive relaxation because this thing needs to go to 0 as q squared. So instead you write down a current, we call this capital J, that itself would be the divergence, and that's the generalization of kind of this linear version of just dH by ds alpha. And in here, you would have potentially also a noise field. So I would now write down a equation for ds alpha by dt, which is the divergence of this current. Okay? So my noise needs to show up in the current, so overall I still have this conservation law. So continuity equation is fine. It looks a little more complicated than here because I have nonlinear terms in this derivative. The leading term is just S alpha, so the linear term is like that. And there is a conserved noise in the business. Is that making sense? So if I write this out, I would get ds alpha by dt now going to be d and the Laplacian in front. Right? So I'm just combining those. And so this gives me d Laplacian, and then the functional derivative of S alpha of h by S alpha of x and t, and then noise, zeta alpha, where zeta alpha, by comparison here, is the negative divergence of this eta. I call it conserved precisely because of this. If I'm sending the wave vector to 0, there will be no noise, and there shouldn't be, because the q equals 0 component needs to be conserved. So here q equals 0 goes away, here q equals 0 goes away because of this, and so the q equals 0 wave vector component ds of 0 by dt is 0. That's why I call that, that's jargon, conserved noise. Okay? And it works by construction because we put the noise into these fluctuating currents. But the whole thing satisfies this continuity equation, so we're in good shape. Now I can write down the correlations for the zetas, right? So this is still 0 because this doesn't matter. And then for the correlations, let me just drop indices here on this side. I get a divergence on x and a divergence on x prime. I can combine that by just a negative Laplacian on x. So I'm going to write this as minus 2d kt and a Laplacian on x acting on these delta functions. And somewhere a delta alpha beta. So that's the noise correlation that's just equivalent to this one. So this is assuming that the etas were just Gaussian white noise. Okay? Now again, this is assuming I'm relaxing to thermal equilibrium. I'm just not relaxing by uniform relaxation rate, but diffusively. Names to this. This equation here is called the time-dependent Ginzburg-Landau equation, for the obvious reason that we started from a Ginzburg-Landau functional and we just make a time-dependent theory of it under the simplest approximation of only relaxational dynamics. And so it's also called relaxational kinetics. In 1977 or so, Bert Halperin and Pierre Hohenberg wrote a really nice review of modern physics summary of critical dynamics, and they just listed different models by alphabet. That's the simplest one, so that came out to be model A. And you know, for interesting sociological reasons, this model A terminology has survived, so we still call that model A. Or again, time-dependent Ginzburg-Landau equation. Now you can guess that the next simplest version for conserved order parameter, this is called model B. If you forget the noise, this is a well-known equation too. It's called the Cahn-Hilliard equation. Shows up a lot in coarsening and the like for conserved fields, metallurgy and the like. So it's also a noisy Cahn-Hilliard equation. Same thing. But because model A and B is fastest, I'm going to refer to these most of the time. It's just model A and B. Now also because I like to be lazy and not treat these two independent models separately, you can actually combine those with a little formal trick. And the formal trick is to rewrite D by D with an I gradient to some power with a formal exponent A, where A is 0, so this thing is absent for model A. And so I just get back to model A. Or A is 2. If A is 2, this gives me a Laplacian with a minus sign. And so that's model B. If I do this kind of formal replacement in this equation here, so I'm going to write this, and apologize for this, but need some space in front. Then this is both model A and B combined. Here also. Okay, so that's just a shorthand. Instead of writing down the analysis twice, I'm just doing it once with this introduction. Okay. I'm going to analyze this in a linearized limit. And in the jargon, this linearized theory is called the Gaussian model. So if I'm in the disordered phase, what linearization means is I'm just going to keep things that are linear in these fluctuating fields S and H and all that, which means I'm going to throw this one away. In the ordered phase, you have to first expand about the spontaneous order parameter and then throw things away. If you want to know how that works, I think I have that's on today's problem set. We might discuss that later. So this is the linearized theory. We just throw the nonlinear term away. That's major cheating because this was driving the phase transition. The nonlinear fluctuations are really important in giving us the correct critical exponents, right? So what this is going to give us at best is a mean field description, and that's exactly what it's going to give us. So we're just going to get some kind of, truncated version of the theory, but it still gives us this feeling, and we'll see how critical slowing down shows up and how that differs for the cases of non-conserved and conserved order parameters respectively. Yes, so you could do that. What I really mean by this is that S of Q equal in 0 and time does not actually depend on time. That is conserved order parameter. Or the Q equals 0 component is the spatial integral of S of X, right? So the total order parameter, the integral of the order parameter density over all space does not change. As I said, if this were a ferromagnet, that means the total magnetization is fixed in time. Okay? In wave vector space, it means the Q equals 0 component is fixed in time. That's what I mean by conserved. And microscopically, it would be under classical dynamics, the Poisson bracket of S with H would vanish. But this is not a microscopic Hamiltonian, so you have to be careful. Okay, are we good? All right, so let's go through that analysis. I'd like to keep those. Maybe I actually like to keep this one too. Let me just continue here. And I'll be careful not to entirely erase the bottom line there because I'm going to need it. So what I'm going to do is I'm going to go into Fourier space. Because once things are linearized, the issue with this equation are all these gradient terms. And in Fourier space, they become nicely diagonal because what happens is I need just to replace the I nabla by Q. Okay, actually minus Q. So if I do this in Fourier space, this is the Gaussian approximation for in the disordered phase. What is going to happen? The time derivative is going to become a minus I omega. Then I'm going to take everything that comes from this bracket, write it in Fourier space, throw it on the right-hand side. So this thing here is just going to be a dq to the a. Right? Because the I nabla is just giving me a q. And then this is going to be multiplied by tau minus Laplacian squared, so that's tau plus q squared. And I've thrown away the nonlinear term. So this one, all this gets just multiplied with the Fourier component of my order parameter. And then on the right-hand side, what I have left with is dq to the a, Fourier component of a potentially driving field, external field, and Fourier components of these noise fluctuations, stochastic forcing. So I need to specify what now happens to these. Well, even in Fourier space, of course, their average is 0. Well, I need to worry about the correlations. So Q and omega, Q prime and omega prime. So what is that going to be? Well, the prefactor is obvious. That's just going to be twice dkt, again, Einstein relation. This thing gives me Q to the A, right? Nothing for model A. And there was a negative Laplacian for model B, and that negative Laplacian gives me Q squared. So that's all fine. And then I need to, and of course there's a delta alpha beta. This is diagonal in the components of the order parameter in disordered phase. And then I need to Fourier transform these delta functions. So we get spatial and time translation invariance, and that spatial and time translation invariance translates into factors of 2 pi for time delta omega plus omega prime in the conventions I was using. And in space, the 2 pi to the d delta q plus q prime. So the negative q is actually, so q needs to be equal to minus q prime, omega needs to be equal to minus omega prime for this to give me a finite answer. You can very easily check that, it's straightforward. Okay? But that, and likewise that, are just consequences of spatial and time translation invariance. So actually these functions are only functions of one frequency, one wave vector, as here they were only functions of the position difference and the time difference. Yeah, it's 2 pi to the d from that delta function and 2 pi from the frequency delta function. Not really important later, but that's what it is, okay? The Gaussian approximation is the linearization we through this term away. Right? Because you can't actually deal with it exactly when you keep it. But you can deal with it approximatively, but let's not worry about it. Now, once we have that, I can pick up my laser and get rid of this one. So now we can very easily compute the response function chi alpha beta of q and omega. Because that's just the expectation value of s divided by h. Actually ds by dh, but since everything is linear, it's just s divided by h. So it's really just you divide this thing over here, divide this thing over there. Since I take the expectation value, I need the expectation value of theta, but that's 0. Right? So this is what I'm doing. And you see, this only gives you a non-zero answer if I kept my indices, and then the indices here are the same. So this is going to be diagonal. I'm going to call that chi naught because it's the Gaussian theory. It's going to be diagonal. And I'm only getting any, yeah, that's it, actually, that's good enough. So that's what it is. And this chi naught of, let me reinstate the tau so we can look at the scaling form, takes the form of dq to the a, right? Because this is, I'm dividing through with this one, dividing through by h, so I'm left with dq to the a on this side. And downstairs here I get minus I omega plus dq to the a, tau plus q squared. So that's my dynamical response function in this limit. And if you've looked at this, it's essentially the dynamical response function of a relaxing quantity where the relaxation rate is all this. Okay, we'll explore this in a second. Let me get this into scaling form. Want to get this into scaling form, I'm going to pull out an overall factor of 1 over q squared, and I'm going to divide through the whole mess by dq to the a. So when I do this, I get a 1 upstairs, I get a minus I omega by dq to the a downstairs, pulled out this other factor, so that's actually 2 plus a. This is down here, pulled out a factor of q, so here I just have a tau q squared, and there is a 1. That 1 used to be that q squared. Okay. So again, I'm dividing out this one, and pull out a factor of q squared. So tau over q squared plus 1 minus I omega divided by dq to the 2 plus a. And now we just need to compare with the scaling form. This was really lucky. I got these things on the same line. I have to celebrate that because that's basically impossible to achieve. So I can just compare these now. And what you see is that the Gaussian mean field exponents do turn out to be eta equals 0. There's no eta correction here, as I advertised. This should be of the form psi squared q squared. So this tau needs to be psi to the minus 2, or psi needs to be tau to the minus 1/2. Right? And so we said that psi diverges as tau to the minus nu, so it tells me nu is 1/2. But it also tells me this should be omega divided by q to the z. So the dynamic exponent here is going to be 2 plus a. This one is half. Point. Oh, how do I get to nu? Okay, so this here needs to be 1 over q squared psi squared, because my scaling function should be a function of q psi, right? Q should always come with psi. So that tells me 1 over psi squared needs to be tau. So psi is tau to the minus 1/2, right? I just said that, but it's a little faster to algebra in your mind, so that's good. Okay, so we find for model A, the dynamic exponent is 2. And for model B, it looks like 4. What does that actually mean? If you want to know what that means, let's Fourier transform back into time. So I'm keeping Q because the Fourier transform in Q is a little more involved, but let's look at the time behavior. So how does this thing look, right? So this is in frequency space. We looked at this thing in complex frequency space. I have a single pole that sits at minus I omega dq to the a or somewhere. Down there. Okay. And I'm trying to do, if I go to Fourier space, I need to do an e to the minus I omega t integral. So I'm not going to actually do it, but in our minds, this is what we're going to do. So we try to integrate along the real axis here. But at this point, complex integration is again your friend, as it was in Sid's talk yesterday. And you want to either complete the contour this way or maybe that way. Since I have an exponential there, as I go to large imaginary parts of omega, if I choose rightly, the contribution of this semicircle doesn't contribute. Choosing rightly means if t is negative, I need to get to positive imaginary parts of omega, right? Because minus t is positive. Positive imaginary parts gives me I squared times something positive, which is negative. So I have to close this contour upstairs for t less than 0. There's no pole involved, so I'm getting 0, which is good news. It just means we haven't fouled up because this needs to be a causal quantity. It needs to be proportional to theta of t. So good news, it's proportional to theta of t because for t less than 0, we're getting 0. For positive time, for the same reason, we have to close the contour downstairs. We get it minus 2 pi I, and we get the residue at this pole, which just means we need to insert, as I said, the minus I dqa tau plus q squared into e to the minus I omega t. So you're just getting, with the right factors of 2 pi taken care of, we get a dq to the a, and then e to the minus dqa tau plus q squared and t. Right? So you see that the characteristic relaxation time is the inverse of that. So let's be away from the critical point where tau is positive. And if tau is positive, we really don't need this term here. And we see for model A, we just get 1 over d tau, where this is 1. So relaxation time does diverge as I go to tau equals 0. How does it diverge? Well, if tau is 0, I get 1 over dq squared. That's the dynamic exponent, q squared. So a fixed constant relaxation rate is transformed into something that's basically diffusive. So you get a fixed relaxation into, at the critical point, replaced by diffusive relaxation. I think someone just asked me that. That's the answer what that means. Okay? For model B, we start out with diffusive relaxation, where this is the relaxation rate, 1 over tau dq squared. So the effective diffusion rate is d tau. Right? But that vanishes as tau goes to 0, and we need to keep this term, and we get this replaced by 1 over dq to the 4th. So subdiffusive relaxation, much slower than diffusive. That is what happens for conserved order parameter. And so you see the fundamental time scales in both cases are quite different. Okay. Questions to here? So now I'm hoping that critical slowing down dynamic exponents make a bit more sense because we have a concrete example to worry about. All right. One more thing we can easily do is compute in the Gaussian approximation the dynamic correlation function. And so for that, we like to have S alpha, S beta, and take the correlations. We do that at vanishing fields. I can forget this term. So I need S alpha, S beta. S alpha is really just the noise divided by this square bracket. S beta is the noise zeta beta divided by this square bracket at different frequency and different wave factor. Okay? And so as I do this, I'm going to find something that's again diagonal and that satisfies all these factors. And some function C naught of tau, Q, and omega. And that function is just going to be the product of two of these inverse square brackets. So it's going to be minus I omega plus dq to the a tau plus q squared. And another factor like that. And the noise correlation strength in front. So another factor like this with q prime and omega prime. But omega prime has to be the same as minus omega. So I'm getting this multiplied with its complex conjugate, which means I just need the absolute value of this. And so this gives me omega squared plus all this stuff squared, because that was the imaginary part, that was the real part. And you can bring this back into the dynamic scaling form as well. So I need to pull out an overall factor q to the 4, and you get q to the 4 minus a. And I was claiming here that the overall prefactor should be c plus 2 minus eta. Eta is 0, c is 2 plus a, so I get 4 plus a here. Works fine. So you can check that. Let me not walk you through this. And the static correlation function will just be this tau plus q squared. Let me write down the time-dependent ones just so we have it, but not derive it. This will have two poles. We'll have a pole here and there. You can pick either direction. There's no causality. You get contribution from either of these poles, combine them, and you end up with AT, which comes from the Einstein relation, tau plus q squared, and you get the same type of exponential. And the absolute value of time. Because the correlation function is symmetric in t to minus t, and so that is what you need to have. You can check that, it's straightforward. And then if I say t to 0, I told you that's the static limit. So this is the static correlation function. That's the Ornstein-Zernike correlation function. Some of you might have seen before. Okay. And again, it basically encodes eta 0 and nu is 1/2. So am I going too fast? Am I going too slow? So it's rather fast, not slow. Because it's much slower than I hope to go. So I will not speed up, I'll just leave out some things, okay? Yeah, I sense that I shouldn't go faster than this. Are you following me roughly where we were going? I'm not doing all the algebra bits, but main points, good. All right, so this is the Gaussian model. What the Gaussian model tells us is the phenomenology is really showing up. We do get critical slowing down, we can infer dynamic critical exponents. They are very different for conserved and non-conserved order parameter. So it's important to take that into account. The static universality classes is splitting up into different dynamical universality classes depending on conservation laws. Okay? In thermal equilibrium already. So let me tell you what happens if I include fluctuations. And I can do this here. So that's not going to be a derivation because at this rate that would take us another 2 weeks. So what happens with fluctuations? Let me vaguely call this fluctuation corrections. It's actually not small corrections, okay? So it's just the effect of fluctuations. Well, the first thing you can kind of think of what might be happening is if I stare at this thing downstairs here, tau plus q squared, that is the static thermodynamic sustainability that shows up downstairs. So maybe I need to fix this. Instead of writing q squared, I really should write q to the 2 minus eta. So heuristically, that's a nice Greek word is for you wave your hands, flap them really hard, and claim this makes sense. Okay? Educated guess, more or less educated. Maybe I should really replace q squared by q to the 2 minus eta. Because really what these things are, all these tau plus q squareds, the static stabilities. And so really I should fix that properly by the static critical exponent. So if I do this and follow through here, I would just get a minus eta down here. So this would tell you that Z is maybe 2 plus A minus eta. That guess, really, if you think about what that means, assumes, so we've done the statics correctly. We renormalized that just fine by means of whatever tools we have. But we are assuming that there's no separate renormalization showing up for the relaxation rate. That is really what goes behind this. There's no additional kind of long wavelength corrections are coming from there. So this means no independent renormalization. This is just kind of for the experts in here, 4D. And it turns out if I look at model B, that is in fact correct. And it is correct because of conservation law. Renormalizations could only happen in long wavelength limit. Long wavelength limit, there is no relaxation. It's because of the conservation law. So indeed, this doesn't pick up anything. And you can show that formally. I'm just doing a slightly more educated heuristic argument here. And so that means indeed we have Z is 4 minus eta exactly for model B. That's an exact scaling relation that gives you the dynamic exponent in terms of static exponents. For model A, this is not true. There is an independent relaxation. And indeed what happens is if I actually look at this one, what a smaller, eta is positive, okay? So what a smaller exponent means is slowing down. Slowing down, speeding up, I'm always confused. Yeah, slowing down. So fluctuations slow down, make the critical slowing down even slower. For model A, that is not true. Fluctuations actually speed things up. They're still of order eta, but with a plus sign, and people write this by a correction factor C, which is positive. And if you compute this correction factor, to which you need a second order epsilon expansion, it takes the form of 6 log 4/3 minus 1 to lowest order. So, but this is larger than 2. This is less than 4. This is larger than 2. And so here fluctuations speed up things a little bit. It's a not too big correction, but it is a correction. Now, at the end of yesterday's lecture, I showed you experimental data for relaxation of a ferromagnetic film. where they measured Z to be 2.09 in 2 dimensions. So a little larger than 2, and that is, believed to be in this universality class. So it's an Ising magnet, satisfies the static exponents of the Ising model, and the dynamic exponent is this slightly larger than 2 value. How do you fix the C value? Here is just a definition, right? So you say things of order eta, and then you have to compute it. I could have called this whatever. It's the correction from fluctuations. Following this argument, conventionally, people always write this proportional to eta. It turns out, if you do the actual calculation, to this order, it's indeed proportional to eta. And it takes that form. There is no general law, it needs to take that form. Okay? It's just true to this order and works out fine and allows you to live. Yeah, only and only for this particular model. And maybe only to that order. No, not in the finite time allotted to me. Let me not comment on that. We can do that in private. Okay? Actually, a quantum critical point, this doesn't apply because this is explicitly dissipative in what you have. Okay, so yeah, you cannot use that Gaussian approximation. If you want to check how that actually works, you have to expand about the spontaneous order parameter and look into the fluctuating field. Yes, and then this kind of mass term, which looks negative, will pick up things from there, so it's overall positive, because what you're doing is, right, so in the potential here, we're expanding in the Ginzburg-Landau-Wilson potential here, and we have nice restoring forces. You go to the ordered phase, you cannot expand about here because it's unstable. This is what this negative mass means, but you have to expand down here, and you get nice restoring forces. Except, ON symmetric model, there's one mode with restoring force, and there's n minus modes where you have Goldstone modes, as they're called, where you have 0 restoring force. If you go through the first problem on today's problem set, it takes you to all this. You cannot go to really 0 temperature with this model. That's a short answer to your comment. Okay? All right. Well, that concluded lecture 1. So I need to think about what to do about lecture 2. Maybe I just give you a little glimpse in what happens if I drive the system out of equilibrium initially, and then say something about model C very quickly. So I try to do 2 things of the remaining ones for today. And I somehow don't think I will be getting to coupling to conserved modes, which is the second part of lecture 2. And so let me talk about non-equilibrium relaxation. So what we're doing here is we're quenching the system. My figure is over here. We're quenching the system from a high temperature state, like this one, suddenly to the ordered phase, for example, or to the critical point where this is all very flat. Before I discuss those cases, let me just envision what happens if I just quench from basically infinite temperature to this temperature where I'm well above the critical point. Right? So I know what happens. We just computed in this regime the relaxation rates. Right? This is the relaxation time, the inverse is the relaxation rate. It's just finite and happy, and so I don't even need to worry about this. Tau is finite, right? So we're going to see relaxation to thermal equilibrium on that time scale. Okay? So if I'm just within the disordered phase, I'm going to see a relaxation on that time scale. Now, naively, you might think if I quench from the disordered to the ordered phase, I just get relaxation on the time scale down here. No, it's more difficult because some parts of my system will be quenched to this minimum, other parts will be quenched to this minimum. So I get a spatially inhomogeneous configuration where I might get some domains in an Ising magnet will spin up, some domains in an Ising magnet will spin down. So within these domains, you get fast relaxation. but the relaxation of these different domains, them coalescing and coarsening to larger domains will be happening on a much slower time scale. In fact, Sid Redner will discuss that bit, and that goes under the name of coarsening. Coarsening obeys dynamic scaling. Although you're not at a critical point, but it still obeys dynamic scaling. And that's because what happens is the system can't really equilibrate in finite time. There's a diverging length scale in the business, which is the typical domain size. It tends to be scaled to by a dynamic exponent that is not the dynamic critical exponent. It's the dynamic exponents relevant to coarsening. What we just used the same, notation. And so you have a diverging length scale and very slow time scales, and that allows you to get into a different type of scaling regime, which Sid will discuss, so I'm not going to talk about it. I can also quench onto the critical point. On the critical point, I have a diverging length scale too, which is this one. And the length scale goes as t to the 1 over c as well, but let me give this an index c now for critical. Right? So if this were model A or B, this would be 2 or 4. That is the mean field kind of exponents. If I'm in this business, I get this different dynamic exponent. Here, I don't really have domains. I just have large fluctuating clusters. But I still have a diverging length scale. Now, if I have this scenario, I'm not actually really equilibrating. Equilibration times are infinite. And so that means you're not actually reaching stationarity. Order parameter is not going to be a time-independent function. Two-point correlations are not going to be functions of the time differences of both points, but of the times individually. And it turns out, and for critical scaling, for this critical quench, you can actually derive that. For coarsening, you can derive that in certain models, and for example, in the spherical model limit, that things scale as the ratio of the two times. So let me just tell you for critical scaling how the scaling laws look, and I won't discuss too much. So for the order parameter, what one finds is I'm quenching onto the critical point precisely, and I look at the time dependence, and then you find that there is an overall amplitude, there is a time-dependent factor t to the theta prime which grows, and there's a scaling function. And that scaling function comes with this argument such that if I go to large values of that argument, large times, this goes as 1 over the inverse of that argument, so the s naught t to the theta prime cancel out, and I get t to the minus beta over c nu, which I know is the asymptotic long-time decay. So what this scaling function describes is what's called critical initial slip. So as function of time, at large times I would get this power law decay that we discussed already. At small times, if I start with some kind of value close to 0 but not quite 0 like this, I would get a growth. And so this is this t to the theta prime. That's called initial slip. So interestingly, if you start out the system from this kind of basically disordered state, in the dynamics, after some kind of few time steps have evolved, you find this growth, algebraic growth of the order parameter, then some kind of maximum, and a turn over to this algebraic ultimate decay to 0. Not a trivial statement, I'm just telling you that is the case. And theta prime can be computed and evaluated by means of the normalization group. This breaks time translation invariance, as I was saying. And I can write down a similar issue, say for dynamic response functions, and maybe I just leave it at that. And so here we have 2 times. We are looking at first kicking the system at t prime, then observing changes on the order parameter at time t. Right? Because remember, this is causality, so we need to kick the system first and then observe it. And we're looking at the limit where both of these are large compared to microscopic times, but the observation time is much larger than this kind of kicking time, which sometimes is called the waiting time, slightly confusing. because no one has waited for anything. And in that limit, you would find, well, the overall power laws as we were writing them down. In time, this picks up that one. And then there is this algebraic factor with an exponent theta, where the ratio of these times enters. Not a trivial statement, but it is a fact. And then it gets multiplied by kind of standard type of scaling functions. So q psi and q to the c t, something like that. So this is then called the aging scaling regime, where this shows up. For model A, that is all indeed the case. You can compute theta. Theta and theta prime are related to each other. They are non-trivial, and you cannot express them in terms of stationary critical exponents. Just telling you that. So these are independent critical exponents. For model B, that is not the case, because for model B, I cannot have this. I have a conserved order parameter. It doesn't care what I do to it. So theta prime has to be 0. This thing is constant, right? And it turns out that theta is 0 too. And even in the aging scaling regime, for a conserved order parameter, you have no time behavior that is kind of independent from the stationary behavior. And I have more information about this in my notes, but let me just skip those. Say temperature. So you start from an entirely disordered state, like tau infinite, and then suddenly, in infinitely fast time, you end up there, and you have just funny initial state. So the business here, you're starting from an initial state that is fundamentally different from your final state. In the case of coarsening, I'm starting with a system, referring to the next lecture, where you kind of have ergodicity in entire phase space. You can happily explore entire phase space in S. But then I'm quenching to the ordered phase, where actually typically either this regime is accessible or this regime is accessible. So somewhat vaguely, that's called ergodicity breaking. And so that's a very different scenario. If I quench onto the critical point, I really have these very strong fluctuations and things like that, from no correlations to basically infinite correlations. So that's also a very different steady state. Yes, it's still, yeah, that's right. Correct. Yeah, sure, but there might be other hydrodynamic modes. We'll talk about that, actually. Well, kind of all of them are, maybe, but, as sometimes they work actually even far away better than you might anticipate. There's magic in place sometimes. Yeah, this justification is close to TC. Even Ginzburg-Landau theory, this for superconductors works amazingly well, even far away sometimes from TC, and sometimes you just luck out. So it's justified near TC, all these things, but sometimes they actually work better even far away from that. It's still a long wavelength approximation, but yeah, let's keep that statement. All right, let me try to walk you quickly through model C and D. Right, we have A, B, and then C and D. This behavior. Yeah, I mean, how do you get there? Highly non-trivial story. I didn't tell you that. I just told you what the answer is. You have to do short distance expansion in time. It's basically boundary critical phenomena where you worry about this time translation invariance. So you have the time equals 0 surface. You need to treat that separately, and it's a longer story. But I wanted to show you that phenomenology because it's actually quite important. At least we've played with this for the last decade or so, and we found it very useful in characterizing things. So I could not refrain myself from mentioning that. Okay, let me quickly walk you through model C and D. Maybe can we do this in the tutorial? The new model is not going to be that hard, so let me try to walk you through it. Otherwise, I just sit at home in despair and cry because I have really nothing covered. So this is just for my sanity. Okay, so we couple the order parameter to one scalar field. And really for sanity, we need to do this because we know that at least the total energy is conserved. So we know there always has to be one other conserved quantity, okay? And that's the energy density. So I'm going to call that rho, and we're thinking about the energy density. So what I need to do is I need to modify close. I'm almost on the same line. I need to modify this Hamiltonian by adding terms where I have the energy density in there and how it couples to the order parameter. And I'm going to do this coupling in the argument that, rho itself is non-critical. So all I need to do is the lowest kind of order terms in rho, and I need to couple it to S, satisfying the symmetries in S. So there's going to be an overall coupling C. There's an integral. And the lowest order term I can do is rho of x squared. And so that would be a term that gives me a Gaussian correlation function, just the inverse of that. We just saw the Gaussian correlation functions for S were tau plus q squared. So aside from the 1/2, it's just the inverse of what sits here. So this is just the correlation for the rhos. If these are energy fluctuations, that's essentially just a specific heat, okay, which is why I called it C. It takes up some corrections in KT and stuff, but essentially it is the specific heat, which means C is essentially scaling as tau to the minus alpha as I approach the critical point. And then we need some coupling here of the energy density to the order parameter. And the simplest we can have is a rho S squared. We cannot have something that's linear in S because of ON symmetry, and so the simplest one is this one. So to see what that does statically, not worrying about dynamics, I can just look at this and see that rho shows up only linear and quadratic. What I need to do ultimately is I need to compute partition functions, which are integrals of all values of S, all values of rho. Since this is bilinear in rho, I can just integrate it out by a Gaussian integration. So which means I can look at any space point, and I'm dropping the space point, and look at e to the minus rho squared plus g rho s squared, and divide by 2c, and kt, because that sits in my Boltzmann factor. And so that's what I need to do into the integral. And all you need to do is complete the square for this thing. Right? I'm sure you can do that. It's Gaussian integral, complete the square. And what you find is this is going to be proportional to the square of g, square of s squared, and then collect the factors, you get 8c kt. So this is of the form of something over kt with this stuff. So I can re-put that into my Hamiltonian. If I put this back into the Hamiltonian, it's just going to modify this fourth order coupling. And if you collect the terms, it's going to modify to u by u minus 3g squared over c. So that's all this is doing statically. But the value of u doesn't matter. As long as it's positive, it's going to approach a fixed point value at the critical point, so statically none of this matters. Okay? Well, this is negative. If this blew up, you're in trouble. What c goes is tau to the minus alpha, so this actually even vanishes as you go to tc if alpha is positive. Dynamically, things are a little more interesting. So this gets a bit borderline, but let me still try to write this down. So dynamically, I'm just going to assume still relaxational kinetics for the order parameter. So it looks like model A and B, but now with this coupling. For the conserved density, I'm just writing down a model B-like non-critical thing because it's a conserved field. Right? So I'm going to get E as alpha by dt where this is now called model C, non-conserved order parameter, and the conserved version is called model D. And then I need a d rho by dt, and I need some relaxation constant, call that lambda. I need to have diffusive relaxation, and I need to have dh by d rho, plus some noise eta, which is conserved noise. Now this relaxation constant, if you think about it, dh by d rho is going to give me a 1 over c, And so lambda over c is like the diffusion constant for this conserved field rho. So heat diffusivity is not usually called heat diffusivity, but thermal conductivity. So this is the thermal conductivity. And it will scale as tau to the alpha because 1 over c scale is tau to the minus alpha. Okay, actually I think that might be good enough to get to the exponents. Right. Maybe yes. Okay. So let's assume what is called strong dynamic scaling, which means we effectively have the same dynamic exponent z for the order parameter field and the conserved density rho. That does not have to be true, but let's assume that. If we assume that, we can actually figure out what z is if that coupling stays into place. And that works as follows. My dispersion relation for this heat diffusivity here is diffusive, as we said, tau of tq squared. And as I just said, this is basically tau to the alpha q squared. And then some scaling function. What it scales is tau to the alpha. That's its temperature dependence. On the other hand, for the order parameter, we have q to the c and the scaling function that depends on q psi. Right? Psi goes as tau to the minus nu. And I would like to have this temperature dependence here to be the same as this one. Okay? So I need to have a behavior here that goes like this, q psi to the minus 1 over nu. And I need to get plus alpha, so alpha over nu. The minus sign, I was right. So this would give me the same tau dependence. And then I can read off that this 2 needs to be the same as z minus alpha over nu. So it tells me that z needs to be 2 plus alpha over nu if I have the strong dynamic scaling. And so with this, I can actually conclude my lecture only 3 minutes over, because this alpha is actually positive if you're in the Ising universality class, one component order parameter. And this is in fact true. And you get strong dynamic scaling, and the coupling to the conserved quantity modifies the scaling exponent for model A, which is c and a little larger, to 2 plus alpha over nu, 2 and a little larger. If I'm in more than one component system, alpha is negative, and it turns out this is irrelevant, and you get decoupling. The order parameter just goes as model A, and the energy fluctuations do their thing. It's called weak dynamic scaling, different dynamic exponents, and I can really ignore the conserved quantity and just play with model A. If I'm the conserved regime, there's no way to get these things to fluctuate on the same time scale, because that's 2, and that's q to the 4th, basically. So that is always decoupled. For model D, you just really, there is no model D. It's basically model B and period. So that's one example where you can analyze fairly quickly, and a little quicker than I wanted to, I admit, but we can fairly quickly analyze the relevance, the importance of a coupling to a conserved field. Okay? And it's by arguments like that that you can mess with it, and of course you can make this more rigorous by actual calculations rather than heuristic hand-waving. But I'm not going to do this in this course. Okay, so tomorrow we'll worry about reversible couplings, and I'll quickly walk you through that, and then we go to maybe generic non-equilibrium systems. If you have a question or a comment, I'll take it. Yes, there is. As I said, I mean, in principle, any magnet, in your Ising magnet coupled to an energy density, you might see this. If you have phase separation of scalar densities, it's, liquid, well, a two-component liquid is described by something else, but yes, there are realizations for that. But as you see, it's really only relevant for scalar fields. So for the Ising model, you technically would have to worry about it. But not for planar magnets, not for Heisenberg magnets. which is why we usually never talk even about this kind of dynamics for magnets. But we have to worry about other things for magnets. We're going to talk about that tomorrow. Any other questions?